Hello and welcome to our Logism Simulator series. My name is Castillo from CPE107L Section B1, and today we're going to analyze our T flip-flop and determine its function and its operation on the Logism counterpart. So our T flip-flop stands for toggle flip-flop, which operates where if the toggle is on, then it will take the prime of the input Qn. So we have here our truth table. If clock is 0, then we will only, and toggle is, if clock is 0, then our toggle state will not matter and it will only store whatever value is in Qn. And if clock is 1 and toggle is 0, meaning no operation will be done, and we will only store whatever is in Qn. But if toggle is 1 and clock is 1, we will now perform a negation of the Qn input, which is the present bit. So in our characteristic table right here, as you can see, this is the table where we assume the state where the clock signal is always high, or the cases when the clock ticks are always high. So as you can see, if Qn is 0, is 0, we will retain what is stored in Qn on the next output, which is Qn plus 1, then we will have 0. And if toggle is 1, we will take the prime of 0 of the present bit 0, and now we have a next bit of 1. If toggle is 0, we will retain the present bit 1 as output to the Qn plus 1, which is the next bit. And if toggle is 1, we will take the prime of the present bit, which is Qn, which is 1, and output it as 0, which is our next bit for Qn plus 1. And the excitation table is just done to determine if we have the past value, the present value, and the next value, and we want to determine the toggle state, which follows the same rule as the truth table and the characteristic table. And for our logistic counterpart of our flip-flop, we can now use the JKV flip-flop, which can be converted into T, which is done by having both inputs J and K be powered by one input signal, which is T, short for toggle, and the clock will still remain as clock. So to demonstrate again, if clock is 0 and whatever value of T will not matter, and we will only store what is stored in Qn. But if clock is high, but if toggle is on, and for the cases where clock ticks high, we will take the prime of the present bit and output it as the next bit. So right now we have a present bit Qn as 1, and if we tick this off, as you can see, we will store the present bit 1, and if the clock ticks high again, the present bit 1 was now changed to the prime of it, which is 0. So as you can see, it will alternate on 1 and 0 every time the clock is ticking high signal. So as you can see, 1, it will change, 0, it will not, 1, it will change, 0, it will not. So now for our shift register, since we now have our T flip-flop right here coming from the JK flip-flop, we can now convert it to D flip-flop, which is more commonly used for shift register. So in order to convert that, we will now take the characteristic tables of T and D flip-flops. So again, the characteristic table is derived when is assumed that for the cases where the clock signal is high, so meaning our flip-flops will operate. So in D flip-flop, it operates as differently than T, in a way that if our present bit is 0 and our D input is 0, it will store whatever value is in the input D. So as you can see, if Qn is 0, D is 0, following that rule, we will store 0 because we will store 0 on the next output Qn plus 1 because our D input is 0. And the cases where Qn is 0, D is 1, we will store 1 as our next bit. So as you can see, Qn plus 1 is 1 on that time. And if Qn is 1 and D is 0, we will store 0 on our next bit. To put it simply, whatever input is in D, then that value will be stored the next. So that's how the flip-flop operates. So, but now we want to convert our T flip-flop to D flip-flop. So we can do that by taking these two columns and this column. So we will treat our D input in our D flip-flop as T prime. So as you can see, this is our toggle state, so to speak, and the output T is now our next input as Qn plus 1. So to convert, to determine this, we will now apply the operations of the toggle flip-flop. So if Qn is 0 and the toggle prime is 0, then we will retain the value of Qn for our next output, which is 0 right here. And if toggle prime is 1 and our Qn is 0, then following the toggle rules, we will prime the Qn and output it on our next output, so which is 1. So if toggle prime state is 0 and Qn is 1, we will retain 1 because our toggle prime state is 0. So following again. And if toggle prime is 1 and Qn is 1, then we will take the prime of Qn, which is 0. So if we analyze, we can now simply simplify this operation as a XOR operation. So it is XOR because if the input signals are the same, even, we will output false. But if the number of zeros are odd, then we will output a high value, which is also displayed by the XOR gate. So we can now go back to our the DC counterpart. So we will be using our T flip-flop right here, and we will now use the XOR gate and take our Qn. So this is our Qn and our toggle prime state. So since D or since it is toggle, we can just call it D or simply T prime. So let me just rename this Qn and 24 T prime. And this one will be our clock. So to demonstrate, so since our T prime is 1, then our output is 1. So for every time that the clock signal operates between high and low, our Qn will not change. But if we change our input in T prime and the clock operates in high state, we will now store the new value, which is 0. So as you can see, yeah, so for more samples, so that is how we convert our T flip-flop to D flip-flop. So now we will be doing the shift register, so which is serial in, serial out. So the operations of the serial in, serial out is shown right here. So as you can see, we have our D in. So this is where our values will be input. So serial in, serial out, meaning one by one in and one by one out. So we can now follow this diagram. So and this clock, right? Okay, clock. We can now get our clock. This is. We can now get our clock, our input. Our input right here. And since our Qn prime will not be used, so we just cascade them like that. So yeah, let's make it 5 bits. And we will have our output pins. Right here. To display our stored bits. No. That is for serial in, parallel out. So we can just sorry, produce our output right here. I separate. And so let's see if I want to store, let's say 1,000. Ilan yan? 10,011. So, what if I want to store 10,011? So, we will now place 1, tick it high, then it is stored right here, and change it, and then store again 1. So, we will now operate on starting from our least significant bit, which is the rightmost, then working to our most significant bit, which is the leftmost. So we will now tick again high, ano nangyari? Hindi ko na-connect sa clock yung pangalawa, kaya pala hindi gumagana. Yan. Okay, again, continuing, since we now stored a 1 value right here on our first flip-flop, and if we tick again a high signal, we will now move our previous bit to the next flip-flop and store our present bit, which is 1. So as you can see, we are now shifting bits by bits, which is hence the name shift register, because we are moving the bits in certain way, which is can be 1 by 1 or parallel by groups, which is can be explained later in pipo, piso, and sequel. So continuing, we now stored the least significant bit, which is we are now at state 11. So I want to store 0, so we will now give a high signal on input 0. So as you can see, we now stored 0, 1, 1, and I also want to store 0. As you can see, it moves. Now we have 0, 0, 1, 1, and for our final bit, we just need to change that to 1 and then store it again, and now we have our uh, we now have our sample case right here. So let me just make it bigger so you can see. And so as you can see, following right here, we have a state value of 1, state value 0, 0, 1, and lastly 1. So that is for our shift register serial in, serial out with the use of converted T flip-flop into D flip-flop, and moving on to our SIPO, which is actually the same. So we can just copy paste this to our SIPO, but this time we will now have the same number of inputs and the same number of outputs as the number of flip-flops. So there. So let's try again. We want to store our value 10,011. So again, we need to store 1. Give it on the first cycle, then store 1 again for the second cycle, and then store 0 on our third cycle, and store 0 for our fourth cycle, and store 1 for our fifth cycle. So as you can see, we now have, we input 10,011 one by one and output them at the same time, which is hence the name serial in and parallel output. So the difference here in CISO, since CISO is serial out, so meaning the number of bits, so the number of memory, the number of bits stored, the output, the clock signals or the clock operation will depend on the number of flip-flops present in your circuit. So here on our first 5 cycle, we now stored the value 10,011. So in order to export our value right here, we need 5 high ticks again in order to export them to our circuit. So, but in the case of serial in, parallel out, we will only need 5 high signals, 5 ticks or 5 cycles from our clock. So at the fifth cycle, we can now use the register right here and take whatever the output is here. So for the case of parallel in, parallel out, so it is slightly different than the previous. So as you can see, we have parallel in, parallel out. So we will store this. No. Wait. For our parallel in, parallel out, we can, since our D flip-flop takes whatever input it has and store it, so we can just simply use that. So we will, with just few modifications, so we will have 5 different inputs for our circuit. So basic sum. So this circuit, the parallel in, parallel out, is also known as a storage register or the buffer register, because technically we're adding a delay by adding an operation which is stored in the register, which is basically storing them at the same time. So with that, we can put this into north. So uh, um, and so as you can see, we have 5 different inputs for our 5 outputs. So we can output them the same. So we will, let's say we want to store 1011 at 10,011. So we simply change the inputs of every flip-flop, and in one tick, we instantly stored the value right here as in the output. As you can see, 10011. So that is how parallel in, parallel out shift register works. So for our parallel in, serial out, so for our parallel in, serial out, so we will just follow this diagram right here. So basically, if the switch state, we introduce a new input, which is a switch. So if the switch is 0, meaning it is in load mode or in storage mode, so it will store the values that is presented in inputs B0, B1, B2, B3, and so on. But if the state is 1, then we are now loading, or technically outputting, the values that was stored in our flip-flop. So let me just create this one in our logisim counterpart. So let's see. So we need a switch that is a NOT gate, AND gate, and OR gate. So is so okay. So it is ANDed, the negation of it is ANDed by the input. So let's sound and new input right here. An on, and then this one, the original is used. Okay, the output is here. Start that here, and for our next inputs, wait. Tama pala yung ginagawa. Okay, now we need and then this one will be right here. Okay, tama. Ito. And there. So let's so 1, 1, 0. Okay. So now we completed our parallel in, parallel out. So to demonstrate here, as you can see, if the switch is 0, then the second gates will be 1. So the even AND gates 2, 4, 6. So that will be the AND gate that will operate. So and then the next odd number AND gates, which is 1, 3, 5, will simply be 0. So since the input is 0 right here, so if anything ANDed with 0 is just 0, and anything ORed with 0 is just that anything, or is that value. So since the even gates will operate right here, so we are now storing the bits that is in B0, B1, B2, and B3. So to demonstrate that right here, so I simply, let's say I want to store an alternating values of 0, 1, 0, 1, 0, 1, 0, 1, 0. So let's see, let's pick a high signal on our clock, and it is stored. So as you can see, this one is 0, this line is 0, this one is 1, this line is 0, this line is 1, and our output is 0. So let's now toggle the switch to unloading mode. So for every ticks of high signal, we are outputting 1 bit at a time. So on our first cycle, we output 0 because it is the last bit right here. So that is automatic. For our next tick, we are now outputting a value of 1. For the next bit is the value of 0. For the third cycle is 1. Is 1 right here. And for our last cycle is 0. And as you can see, our flip-flop is now empty, which is 0, 0, 0. So with that we can now introduce new number. So let's say an alternating of a value of 10110. So let's see. First, we need to store it by toggling the switch to 0 and tick once for our tick our clock once on high once. So we now store the value 10110 on our register. And for our output, we tick the switch to high, and then we now start outputting. So on our first cycle, uh, for our during our low signal, last bit right, the rightmost bit right here is automatically outputted right here on our output pin. So on our first high tick, we output 1. On our second high tick, we output another 1. For our third high tick, our output is 0. And for our fourth high tick, we output a value of 1. So that concludes our shift register parallel in serial out. So I think that's all for today for our T flip-flop. So again, I converted the JK flip-flop to T flip-flop and T flip-flop to D flip-flop and used that converted D flip-flop to make the 4 types of shift register. Again, my name is Castillo from CPE107 Lab Section B1 for Group 4, and thank you for watching.